Okay, we're going to cover section 3.2, which is going through the concepts of addition and subtraction. So we're going to look at the formal definitions. We're going to address different methods for doing these and some visualizations. Okay, so let's start with the definition, which you think would be easy, but is not easy. Defining addition and subtraction is not always all that straightforward. Okay, so if a set R has R elements, so remember a set is just a collection of objects, and R elements then would be how many members there are in that set. So here, let me just do a little drawing here. So let's say this is the set R, and then they also refer to a set S, and they tell us that they're disjoint. Okay, so let's say that the members of R look like this. And then the members of S, let's say they look like this. Little squares. So X's and squares. Okay, great. So R would have, little r would be how many elements there are, how many members there are. In that case, it would be 5. And little s would be 4 because there's 4 members of that set and they're disjoint. So R plus S is the number of elements in the union of these two sets. So union, you might remember, is bringing the sets together. So this will be R union S. And here, let me zoom in a little bit so I can do a better job with this picture. So that would mean that we'd be taking these X's and combining them with the squares. And R plus S would be the combined number of members that are in here, which are 9. So that's the definition of addition. I know you're like, wow, that's kind of amazing, but it is how we would define it. Okay, so let's start with visualization, and we'll pick up with what we talked about in 3.1. Let's use base 10 blocks. So here again, I'm going to zoom in a bit, and let's try to do a visualization using the base 10 blocks to add 524 and 639. So here, let me start with 524. Now, 524 is 500. 24, so 2 10s and 4 1s. So we're going to use 500s blocks. Now, for the sake of not trying to just take forever to do this, I'm going to do each 100 block as an actual giant square, but that square is supposed to represent the 10 by 10 blocks that we talked about last time. Here, I'm just going to draw a big one, but where you had 10 rows and 10 columns, right? Like those. It's supposed to represent 100 little individual squares, but I'm going to just draw it really big as a big box to make my life a little bit easier. So we would have 5 of these. Wow. 5. And then we would need, let's see, 2 10s, which are the skinny little rectangle blocks that represent 10 little squares. So we need 2 of those. And then 4 1s would be 4 little squares. Okay, so that's how we could represent 524. All right, so 639 would be 6 of these 100 squares. I'm trying my best to make them as close in size as possible. Oops. I say that, and then the minute I say that, it like gets worse, right? Okay, here, let me actually put 2 squares down here just because of space. And then I need 3 10s rectangles. And then 9 little 1s. Squares, single squares, to represent the 9 in the 1s place. Okay, there we go. Cool. Okay, so visually then what we have are 11 100 boxes, so 11 hundreds. And then we have, let's see, 5 tens. And then 9, 10, 11, 12, 13 ones. Now, the problem is that's not the answer, okay? And the reason is there is that concept of regrouping where we can, because we have 13 ones, that means that instead of doing 13 single squares, we can trade 10 of them, 10 of these, to become one single rectangle. So that then changes this to be 6 tens. And now I only have 3 ones left over. So my answer is 1163. So I'm reading the numbers here, but I had to first do regrouping before I was able to give the final answer. Okay. All right. So that's usually using the tens blocks. Okay. Now let's talk about different methods for addition. And some of these might be methods you haven't seen before, and they are different than the traditional old school carry the term over method of addition. And it gives students an opportunity to kind of view the problems a little bit differently. So the partial sums approach actually has 2 variations. The first is to write out the 2 numbers based on their place value. So writing out 345, I would write 3 hundreds, 4 tens, 5 ones. And then this would be 2 hundreds, 7 tens, and 8 ones. And then when I add, what I'm adding are the hundreds, tens, and ones. So I have 5 in the hundreds, 11. I just realized I wrote 10 very weird. I don't know what the hell that was. Sorry. Tens, 11 tens, and 13 ones. Okay. But just like before, we are going to have to do some regrouping. So technically, we have enough tens that we can do 100 square. So if I take 10 of those out, I can do 100 square, and I'm left with 1 10, and I now have 6 hundreds. Then I could do that with the ones as well. I can take 10 of those ones and make a tens rectangle, which means I now have 2 tens and 3 ones. So that would be my final answer. 6 hundreds, 2 tens, and 3 ones, or 623. I'm going to cough. Hold on. Sorry. Excuse me. Okay. Now that works fine. It's not too complicated, but there is a cleaner method. And the cleaner method is to actually work within the numbers and work within their columns of place value. In other words, kind of visualizing the tens, the hundreds, and the ones place. So if I want to add these, what I'm going to do is I'm going to start with the 5 and the 8 in the ones place. So that's going to be 13. But because it's not going to fit 13 in that column, I'm going to actually put the 1 in the next column. Then I'm going to add the 4 and the 7, which comes out to 11. And again, I'm going to put the 1 on the 11, the tens place, into the next column. And then the 3 and the 2 add up to 5. And there we go. I should have done these in green, the columns in green, just so that I could draw them all the way down. There we go. So what we're left with is 623, which is, of course, what we got just a second ago. So that's kind of a nice, clean way of doing it, just kind of lining them up in their columns. And when you don't do 2-digit numbers, whenever there's a second digit, you put it into the next column or the next place value. Okay. Let's try that again, but with a couple different numbers. And in fact, maybe it's worth pausing the video, giving it a shot, and then seeing if your answers match. Okay. But I'm going to go ahead and work through it in case you decide you don't want to do it that way. So 694 and 539. Actually, never mind. I take it back. Here's what I want you to do. I want you to complete this problem and send it to me. So just snap a picture of it and send it to me. That way I know that you understand this concept and that you completed the notes. Okay. So do the two methods. All right. The two methods we just did up here for the partial sums, do both methods and then send me your work. Okay. Just snap a photo, send me your work. All right. So let's look at another type of addition. This is called the left to right addition, which makes a lot of sense because our language reads left to right. So wouldn't it be nice if we could do our math left to right as well? So I'm going to start with 897 and 537. And I'm going to add them. Okay. And I'm going to start with now the left column, which the hundreds place. So I'm going to start with the 8 plus 5, which is 13. And then I'm going to do the 9 plus 3, which is 12. But then I'm going to take the 1 and I'm going to bump this 3 up to be 4. Since I can't fit 12 in there, I'm going to bump up the next column up to 4. And then 7 plus 7 is 14. So I'm going to bump the 2 up to 3. So my answer is 1434. So what I just did there is called the scratch algorithm, okay, where you change a place value based on having to bump it up or quote unquote kind of carrying a number, but we're doing it left to right. So it does kind of change that. So here, since that's pretty quick, let's do another one. 378 plus 657. I don't know why I spaced that out so much, but I did. Okay, so starting with the left column, that's a 9. 7 plus 5 is 12. So we're going to scratch that, and that's going to become 10. 8 plus 7 is 15. Scratch the 2. That becomes a 3. So our final answer is 135. I'm sorry, 1035 or 1035. Okay, now before we can talk about subtraction, we need to have the concept of inequality. So any two whole numbers, m and n, we say m is less than n, which we write m parentheses n, if and only if there is a non-zero whole number k such that m plus k equals n. So in other words, in order to make m the same size as n, we have to add a number to it to get it to be the same. Okay, so m is clearly smaller than n for this reason. All right, building off that concept, let's write the definition for subtraction. I did forget to mention DEF. I think I've used that notation for you guys before, but definition. Subtraction of whole numbers. So for I think that's supposed to be any, not and. That's funny. Any whole numbers r and s with r bigger than or equal to s. The difference of r and s, which we write r minus s, is the whole number c such that r equals s plus c. And we call c the missing addend. Now, what's kind of interesting is we define subtraction by addition, right? It's the idea that we're missing a certain amount. There's this kind of missing amount for the smaller number, and therefore we have to kind of add it to get to the same amount. Okay, that concept helps us with visualizations. And we have these ways we can think of subtraction when you're kind of going through teaching these concepts. So the first is the takeaway concept. So you have 13 marbles. I don't know why the computer doesn't like that word. And you give your friend 7 marbles. Well, it likes it there. That's so weird. How many do you have left? Okay, so 13 marbles. Let me draw that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 marbles total. So if I give my friend 7 of them, that means I'd give my friend all of these. Boop, taking them away. I am left with 6. So 13 minus 7 equals 6. That's the takeaway concept. Then there's the comparison concept. When you compare two numbers to see how much bigger the larger number is, you have 6 marbles. Your friend has 8 marbles. How many more marbles does your friend have? Okay, so here's you. You have 6, 2, 3, 4, 5, 6. Your friend has 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is the same, meaning your friend has 2 more than you. So 8 minus 6 equals 2. All right. Missing addend. So this is the idea that we need to figure out how much more needs to be added. So let's say you have 6 marbles, and to play in the Squid Games, you need 10 marbles. Squid Games, get it? Okay. How many more marbles do you need? So we want to start with the concept of 10. And 2, 3, 4. 1, 2, 3, 4. Okay, so this is 10 little slots, and you have 6 marbles to fill. 6, and then that means in order to play the game, you would need to fill up. You need those 4 more. So that would display that 10 minus 6 equals 4. And there we go. Okay. The next major thing they like to talk about in this section is the idea of mental math. They really stress this. And so we're going to look at different concepts of mental math, and we're going to be doing this all throughout chapter 3. So the first type of mental calculation is what they call compatible numbers. That's when you look for pairs of numbers that is just way easier to work with. So we're going to kind of do a few different variations on each problem. So let me just write it. So let's say we have 17 minus 12 plus 43. Okay, so first idea is, okay, it wouldn't be too complicated to just pair up those first 2 numbers, right? 17 minus 12 is 5, and then 5 plus 43, that's 48. Okay, that's not too bad. But here, let's try it again. 17 minus 12 plus 43. So it actually, there's kind of a rule about looking for multiples of 10 because they're easy to work with. And 7 and 3 will give us a 10, right? The 7 in the ones place and the 3 in the ones place will give us 10. So 17 plus 43, that adds up to 60. And then 16 minus 12 is 48. Okay, that's not too bad. So there's a couple different ways you could approach it depending on what's most comfortable for you to do mentally in your head. Now, visually, you need to write down what you're doing in your head, okay? But that is how we're kind of going through it. Okay, let's try another one. This time, let's pair up 17 with the 23 because, again, the 7 and the 3 are going to add up to a 10. So those 2 add up to 40, and then 40 plus 12 plus 45. Okay, now I could do the 40 plus 12. That wouldn't be too complicated, but maybe I'd be interested in doing the bigger numbers first because it's as you're getting more math in your head, it's better to get the bigger numbers over with quickly because then smaller numbers are a lot easier to keep track of. So the 40 and the 45 are 85, and then 85 plus 12 is 97. All right, not too bad. Okay, so let's go ahead and try one more. Actually, why don't you try this one? Try and send to me and see how it goes. Okay, so pair them up to what's easiest. Show me the math. Okay, like indicate which ones you're pairing up. Do keep in mind that when you have a minus, you are dealing with some negatives. Okay, so don't forget that. Okay, let's try substitutions. Now, substitutions are ways that we force there to be compatible numbers. Okay, so it usually means we're going to kind of rewrite one of the numbers so that it works. Okay, so let's start with 127 plus 38. So one way we could rewrite this so that it's a little bit easier is maybe to rewrite 38 as 30 and 8. Because 127 plus 30, that's, oops, sorry, I thought that was in red, but it didn't come up red, is 157. And then 157 plus 8, that comes out to 165. Okay, not too bad to do that in your head. Okay, another way we could rewrite 127 and 38 is maybe break up the 38 in a way that I'll get a tens. So what if I break it up as 3 and 35? Because then I can add the 127 and the 3. That'll give me 130, and then 30 plus 35, that's 165. So that's kind of being really clever and trying to force it to be a nice number that I'm adding them up to. Okay, I of course could break up the 127, right? I could do it that way and try to get a nice number. So like I could break up the 127 as 125 and 2. And what's nice about that is the 2 and the 38, that gives me a tens, right? A multiple of 10. So 2 and 38 are going to give me 40. And then 40 and 125 is 165. So there, that's kind of a way to do it in your head. You break up that number and then use it to kind of work it out a little bit nicely. Let's try one with subtraction. Okay. So let's break up the 40. I'm sorry, 46 as 40 and 6. And since it's subtraction, they're both going to be subtractions. So let me just write it like that. I'll drop the parentheses for right now. Okay, so the 163 and 40, that's going to just be 123. And then 123 minus 6 is 117. Okay, not terrible. But if we wanted to, we could do the 160. I'm sorry, the 163. We could break it up as 160 and 3. Wow, I like keep saying what I'm about to write. Can you tell I'm a little tired? Okay, so the 160 and 46, those two subtract to be 114, and then 114 plus 3 is 117. All right. Let's try one more. Let's break it up. Let's be clever. So I'd like to get something where I'll get a tens, right? Power of 10. So how about I break up 46 as 43 and 3? Because then the 163 and 43, they subtract to become 120, and then 120 minus 3 is 117. So this one to me seems like the easiest of the three. They're all correct. There's nothing wrong with any of them. But mentally, it's a little bit easier to do this, in my head at least, than the other ones. Sorry about my dog barking. Okay. Let's go ahead and look at another technique called equal differences. So for this one, it's the idea of adding and subtracting a constant from both numbers in order to make it easier to do. All right. Now, by the way, equal differences, the fact that it says differences, that's an implication that we're doing subtractions. Okay. That's why this is going to work. So it works for subtractions. Okay. So let's say I add the number 2 to both numbers. The reason I like 2 is that's going to make that 18 into 20. So if I add 2 to 47, that's 49. That 18 turns into 20, and lo and behold, that's super easy to do in my head, 29. Or I could have maybe subtracted 7. That would have made the first number 40 and the second number 11, which also is 29. So that's like one way you could do it. Or I could have subtracted 8. That would have worked. Okay. You kind of get the idea. That would have made that second number a 10, but the first number would have been a 39 and still 29. Okay. So that's the idea for equal differences. Let's go ahead and try this one. So let's say this time I subtract 3. I'll make that first number nice and a multiple of 10. So that'll be 50 minus 14, which is 36. Or what if I added 3? That would have worked out really nicely for the second number. So that would have been 56 minus 20, which again is 36. So that's a nice way of doing some of the subtractions, okay? Kind of adding or subtracting the same number. Okay, then they move into approximations. And we use this probably more than any other type of mental math. The idea that we approximated in our head the solution and kind of have a relative idea of what that approximation does for us. So if you approximate two compatible numbers, meaning you're making it so it's easy to do in your head, an easy approximation on like this first example would maybe be to make the 342 into 350 and then add those two together. That's pretty simple. That adds up to 600. Now, because I made the number bigger, I happen to recognize that this is actually bigger than the real answer, right? My answer here is bigger than, it's an overestimate, an actual answer. All right, that's good to know. Then there's the extremely simplistic front end approximation. So that's literally where you take the front number and that's the number you use. So 342, that becomes 300. 250, that becomes 200. So adding those together, 500. So for front end approximation, we get something smaller than the actual number or an underestimate. But it's very simplistic, which is always a good thing when we're trying to do things in our head. Okay, so using that concept here, then this would be 1,000 plus 7,000 minus 3,000. All right, so I'm going to start with the last two. Those two give me 4,000. And then 4,000 plus 1,000 is 5,000. Boom. All right. So that's how you do front end approximations. Okay, the last little bit, it discusses some number properties, which we couldn't really discuss until we introduced addition and subtraction. And we'll again touch on them when we look at multiplying and dividing in the next couple sections. The first one is called the closure property. This right here, the closure property. And it's kind of one of those properties that we'll see quite a few times, okay? So for every pair of numbers in a set, so two things are in a set. If a math operation is performed and the result is also a number in the set, then the set is closed under that operation. Let me give you an example. Let's say we want to add two odd numbers. So we're looking at the set of odd numbers here. So let's grab two odd numbers out of the space. I'll use 3 and 5. Why not? Add them together, I get 8. 8 is not an odd number, which means that the odd numbers are not closed under addition. Because if I add two odd numbers together, I may not get an odd number. So there you go. Let's do even numbers. Let's add two even numbers together. So here, let's pull out 6 and 8. So those two add up to 14. Ah, that is an even number. Now, to make the generalization that from one example, we have proven it for every even number is not a good mathematical technique, but I can tell you, even numbers are closed under addition. But what we did in the first example, or first problem there, is what's called a example or showing something or finding a counter example. So this is what they would call a counter example. meaning we found an example of something that didn't work for closure. So I found two things that when I add them together, I didn't get an odd number. So that showed that the closure property doesn't work for odd numbers. Counterexamples are something we're going to look at in the future. Okay, so are the whole numbers closed under subtraction? So we want to grab two whole numbers, subtract them, and see if we get a whole number. Now let's refresh our memory. A whole number are numbers that are starting with 0 and then going 1, 2, 3, ... right? They have the counting numbers with 0. Okay. So the whole numbers do not have any negatives. So maybe it would be smart if I got an example, or maybe I'll get a negative. Like, let's say I pick the number 1 minus 4. Those are two whole numbers. But when I subtract them, I get -3. And that is not a whole number. So the answer is no. Because I found a counterexample. I gave an example of something that didn't work. All right. There are 3 more properties we want to kind of discuss really briefly. It's the identity property for addition. So an identity is a number that doesn't affect other numbers. And in addition, that magic number that doesn't affect other numbers, when you add it, add 0. So 0 is the identity in addition. If I add any number with 0, it doesn't do anything. So if A is some number and I add 0 to it, I'm always going to get A, no matter what. Then you might have seen before the associative property of addition. This is when you are moving the priority. And I'm going to put priority in parentheses, I'm sorry, quotes, because I'm referring to order of operations. So in order of operations, if you have parentheses, you're supposed to do those first. But when you're just adding a bunch of things, you don't have to do those 2 first. You could do the first 2 numbers, add those first. That's associative property. And we use it all the time without even realizing it. We are using it. We're using it. And then the commutative property is when you could switch the order. Oops, that's not how you spell switch. Switch the order. So A plus B is the same thing as B plus A. Oops. And then we can just do little examples for each of these. So for this one, 5 plus 0 is still 5. For this one, if I do 1 plus 2 plus 3, that comes out to 2 plus 3 is 5, and then 5 plus 1 is 6. But I still could have done 1 plus 2 first and then added 3, which would have been 3 plus 3, which is 6. So they both give me 6. The order where the parentheses go, I mean, the priority doesn't matter. Or if I do 2 plus 3, that's the same thing as 3 plus 2. We can swap the way we write them. So those are those number properties. And we will look at them again when we're looking at multiplying and dividing. Okay, so that's it. Go ahead and send me those problems and you will be good to go. You'll get some points for that.